Welcome to our channel. Subscribe and watch until the end of this video. Polar Aurora. Let's begin by remembering that there are two polar auroras. In fact, we inhabitants of the Northern Hemisphere tend to only remember the one we can see in our winter, which is relatively easy to observe if we move to an area where it is visible. However, in the Southern Hemisphere, the phenomenon becomes visible during the southern winter. Here, organizing a visit to witness the phenomenon becomes a bit more complicated and expensive. We will see later in more detail where and why it only occurs in well-defined areas. It is called the Aurora Borealis, also known as the Northern Lights, when it occurs in the Northern Hemisphere, boreal, while the name Aurora Australis refers to the equivalent phenomenon in the Southern Hemisphere, austral. The two auroras, boreal and austral, happen at the same time, but clearly we will only see the one that occurs in the hemisphere currently experiencing winter. This is because the Earth's axis is tilted by about 23 degrees relative to the plane of its revolution around the Sun, and one of the two poles will be illuminated by the Sun, so we won't be able to see the aurora, while the other will be in darkness, allowing us to enjoy the aurora. The polar aurora is one of the most beautiful phenomena that can be observed with the naked eye in the skies near the poles. This phenomenon is visually characterized by luminous bands that take on a wide range of shapes and colors, rapidly changing over time and space, usually in shades of red, green, and blue, called auroral arcs, caused by the interaction of charged particles, protons and electrons, from solar origin, solar wind, with Earth's ionosphere, the atmosphere between 100 to 500 chem. These particles excite the atoms of the atmosphere, which, after relaxing, emit light at various wavelengths. On August 28, 1859, some auroras were observed over a large area of American territory. In scientific centers around the world, instruments experienced strong and unexplained variations, and spurious currents formed in telegraph lines. The next day, English astronomer Richard Christopher Carrington noticed a group of unusually large sunspots, from which a flash of whitish light emanated, which, after a few hours, produced a second wave of intense auroras. With the Great Aurora of 1859, also called the Carrington event, the models explaining solar activity phenomena quickly evolved. The old hypotheses of high-altitude flashes or light reflected from icebergs were replaced by those more related to solar events and disturbances. It is estimated that storms of such intensity occur once every 500 years. Another event, about half as intense as the one in 1859, occurred in 1960 and caused radio interference across the planet. Experts believe that the costs of a potential superstorm could be comparable to those of a major earthquake if adequate countermeasures are not taken, such as postponing certain sensitive activities performed by satellites, altering air routes, and identifying vulnerable components of networks in advance. Solar magnetic activity, and thus the formation of sunspots, varies cyclically every 11 years. In December 2019, a new cycle began, with a peak in activity expected in 2025. In the past 11 years, researchers have detected about 21,000 solar flares and 13,000 plasma clouds released from the solar surface. In Central Europe, the visibility of the Aurora Borealis is quite rare. However, on the night between November 17 and 1848, the phenomenon was so intense and widespread that it was visible even at low latitudes. In Naples, it was observed by astronomers at the Capodimonte Astronomical Observatory. In Rome, the phenomenon gained significant attention. More recently, the Aurora Borealis was well observed in central northern Italy on the nights between May 10 and 11, 2024, and between October 10 and 11, 2024. What shape does it have? In this image, we can see the Southern Lights Aurora Australis over Antarctica as captured by NASA's IMAGE satellite on September 11, 2005, and superimposed onto NASA's satellite-based blue marble image. The shape of a polar aurora is very varied. Arcs and bright rays of light begin at 100 kilometers above the Earth's surface and extend upwards along the magnetic field for hundreds of kilometers. The arcs can be very thin, even just 100 meters wide, yet stretching from horizon to horizon. They can be almost motionless, and then, as if a hand had passed over a long curtain, they begin to move and twist. After midnight, the aurora can take on a blotchy form, and each blotch often flashes every 10 seconds in a yellow-greenish color, but sometimes the rays can become red at the top and along the lower edge. On very rare occasions, sunlight can hit the upper part of the rays, creating a faint blue color. Even more rarely, once every 10 years or more, the aurora can be blood red. This is dissipated as infrared radiation or carried away by strong winds in the upper atmosphere. Where can it be seen? Due to the geometry of Earth's magnetic field, auroras are visible in two narrow bands around the Earth's magnetic poles, called auroral lobules. Auroras that we normally see with the naked eye are produced by electrons, while those produced by protons can only be observed with the help of special instruments, both from the ground and from space. Later, we will see in detail what happens during the aurora. Auroras are more intense and frequent during periods of intense solar activity, when the interplanetary magnetic field may exhibit significant variations in intensity and direction, increasing the possibility of coupling, magnetic reconnection, with the Earth's magnetic field. Sometimes during the appearance of an aurora, sounds resembling hissing can be heard. On a winter night in Rheen, Lofoten, half frozen, while I was waiting for the aurora to increase in intensity for some good photographs, I was fortunate enough to hear the aurora. It sounded like hearing an organ in the celestial dome, where the sounds come from the entire celestial dome, with no apparent direction. It was a wonderful concert. These are electrophonic sounds, a phenomenon that can occur, though much more rarely, during the appearance of boids. The origin of these sounds is still unclear. It is believed that they are caused by local disturbances in the Earth's magnetic field, caused by an increased ionization of the overlying atmosphere. Polar auroras are often accompanied by radio emissions in the VLF band, known as the auroral chorus. Since the frequencies of these signals are in the kilohertz range, they are audio frequencies and can be converted into sound using a special receiver. The sound produced resembles a chorus of birds, which is how these emissions got their name. Why does it happen? In an upcoming video, we will explore the topic of solar activity and solar wind in more detail. For now, we just need to know that the sun is the origin of the aurora, located about 150 million kilometers from Earth. The appearance of a large group of sunspots is the first sign of intense coronal mass ejection activity. The energetic particles emitted by the sun travel through space, forming the solar wind. This moves through interplanetary space and can reach Earth in 50 hours, at speeds typically ranging from 400 to 800 kilometers per second, driving along part of the solar magnetic field, interplanetary magnetic field. The solar wind interacts with the Earth's magnetic field, also called the magnetosphere, distorting it and creating a sort of magnetic bubble shaped like a comet. The Earth's magnetosphere functions as a shield, protecting the Earth from direct impacts by the charged particles, plasma, that make up the solar wind. In approximate terms, these particles slide along the outer edge of the magnetosphere, the magnetopoles, and pass beyond Earth. However, due to a process known as magnetic reconnection, where the interplanetary magnetic field points in the opposite direction to Earth's, the plasma from the solar wind can penetrate into the magnetosphere and interact with the Earth's ionosphere, giving rise to the aurora phenomenon. It is worth noting that the Arctic zones, possessing lesser magnetic protection, are the most exposed to this phenomenon. Often, for several days after the event, ozone levels can drop by about 5%. Auroras are more intense during magnetic storms caused by strong solar activity. The distribution of aurora intensity with altitude shows that they primarily form at an altitude of 100 kilometers above the Earth's surface. They are typically visible in regions near the poles, but can occasionally be seen much farther away, up to 40 degrees of latitude. The particles moving towards Earth strike the atmosphere around the poles, forming a kind of ring called the auroral oval. This ring is centered on the magnetic poles, shifted by about 11 degrees from the geographic poles, and has a diameter of 3,000 kilometers during periods of calm, growing larger when the magnetosphere is disturbed. Auroral ovals are generally located between 60 degrees and 70 degrees of northern and southern latitude. From a physical standpoint, what happens is, the aurora is formed by the interaction of high-energy particles brought by the solar wind, usually protons and electrons, with the neutral atoms in Earth's upper atmosphere. When these particles reach us, they are attracted to the Earth's magnetic poles. Once captured by Earth's magnetic field, they follow its lines of force until they encounter the first atoms in our atmosphere. At this point, the particles and atoms interact with each other. The valence electrons of the neutral atom can be excited through collisions and will move to a higher orbit. When they are no longer excited, they return to their normal state by emitting photons, light particles. The particular colors of an aurora depend on which gases are present in the atmosphere, their electrical state, and the energy of the particles that strike them. Atomic oxygen is responsible for the red color, wavelength 630 nanometers, molecular oxygen for the green, 557.7 nanometers, and nitrogen causes the blue color. How an aurora is measured? The aurora directly depends on solar activity, so it is useful, before going on a trip, to monitor solar activity and see if the aurora will occur that evening. An index has been created to express the intensity of the polar aurora using the KP index, which can vary between KP1 and KP9. KP1 represents the weakest aurora, and KP9 the most intense. On the picture, a weak aurora in Greenland, disturbed by full moon. Next video will be an introduction to the night photography to provide the necessary information for those of you that would try to get some nice shoot of the aurora, and not only. Thanks to stay with us until the end of this video. If you liked this video, remember to subscribe to the channel to stay updated with the new contents that will be published regularly.